Good afternoon. Just a quick show of hands. How many have at least dabbled with Scala? How about dabbled with a functional language of some sort? How about played with something in the Hadoop ecosystem? How about Spark? Anybody? Okay, so if you raise your hand to those 4 questions, you can go into another session. You're not going to learn anything here. What I'm going to share with you is some of the experience we've had both in the classroom and with research projects and in the local Twin Cities, Minneapolis, St. Paul community, where we've been focusing on big data and data science curriculum for almost 5 years now. But about a year or so ago, we started to get into one of the newest entries to the ecosystem, a big data system called Spark. And Spark is interesting because it's implemented in the Scala language from a language point of view, and also Scala is at least my favorite language to program it in. So I'm going to first take you through a little overview of Scala and then a little bit of Spark and give you some examples of the use of Scala in Spark and just finish up with some experience in the classroom. So Scala briefly is, one thing to know about it is it's a JVM-based language. It can call and be called by Java. That's important because it opens up Scala to 20 years worth of Java libraries, and it enables Java code or Scala code to run anywhere the JVM runs, which gives it platform portability. Relatively new to the Scala picture is a way to compile Scala code to JavaScript that opens up Scala to the client side. There was a .NET effort that has ceased to exist. So one quick way to describe Scala is that it's a richer, more concise Java from an OO perspective, but it also adds a whole bucket of functional programming concepts. So its place in the language space is this intersection between the object-oriented and functional paradigms. It's a very strongly typed language, statically typed language, which often means difficult and cumbersome to use, but in Scala's case, there have been a number of decisions that give you a feel when you're programming with it like you're using more of a dynamic language, not up quite Python, but at least headed in that direction. The name Scala stands for scalable language, and scalable in many senses there. Developed in academia, Martin Adersky, who previously did work on the Java generics library, part of Java 1.5, and also wrote the initial Java-C compiler. So it's been around for a little more than a decade. So just a picture of what I mentioned. In Java, you compile Java with Java-C and run with a Java command on the JVM. In Scala, you compile with Scala-C and run with a Scala command on the JVM. One of my hobbies is collecting diagrams like this for language popularity through time. All these methodologies are flawed. These surveys often contradict each other. So I've just picked one to illustrate what this methodology shows is going on in the language space. Java and C struggling for supremacy here. Depending on what scales you use, maybe Java's a bit on a slow decline. Other languages in kind of second place jostling for position. So we're here to talk about Scala. We're Scala 31st on the list, so it doesn't even warrant a color line on this chart. One of the things I also enjoy looking at is what freshmen in computer science are taught as their initial language. And it used to be Java for a long time. Python has recently edged out Java. But if you look at the candidates on there, there's only one functional language scheme over on the right-hand side. So there's always been a debate in computer science education of whether you start computer science students with an object-oriented view, maybe Java, so they can get an internship and start learning in the real world, or do you approach it from more an intellectual base with a functional programming language? Different universities come to different conclusions, and especially these days, freshman computer science courses not only feed computer scientists, they're feeding other disciplines in engineering and math and statistics and so on. So far I'm not, the Scala people aren't going to hire me for their PR because Scala isn't one of these magic top 10 languages. But a little sign of what's going on in the undercurrent, if we look at job openings for functional language jobs, you see a pretty big, which is a small pool currently, you see a pretty big recent interest in the Scala language over some of the others. So a few pieces of information about Scala, especially if you're coming from a Java base. Very heavy emphasis on trying to Get programmers in the habit of programming with immutable data where you don't store any state. And however, unlike languages like Haskell, which force you to do that, Scala encourages but doesn't force. That's kind of a general philosophy. No semicolons, which sounds like an easy thing to get rid of. Just stop typing a semicolon. I still look back at code I've written a few years ago, and one of the first things that strikes me is how many semicolons I used when I didn't have to. Hard habit to break. Also, you don't necessarily need to specify types in all places. Scala does type inference on some of its values, so it automatically figures out the right type in many cases. And that leads to some of its lightweight feel. Almost everything in Scala is an expression, so other languages have expressions that return values and statements that do not. This also alters programming styles. No need to have a keyword called return. Whatever value you last describe is the one returned. Java has interfaces. Scala has something that looks like an interface, but it's more powerful. It's called a trait and gives some much more powerful mix-in patterns. There's a kind of class called a case class. All you have to do is put the word case in front of the class name, and you get a whole bunch of boilerplate code automatically generated. Toward the end, I've got a little illustration of that. Very powerful pattern matching used in many aspects of the language that leads to very readable code. Null pointer exceptions are a perennial problem in languages like Java. Scala discourages the use of using null and instead encourages a pattern called the option pattern. You can have a void. It's called unit, and it's typed in Java. There is an extremely powerful, some would argue too powerful, type system in Scala, which leads to some of its complexity. There's a feature that's somewhat controversial called implicits. Implicits let you extend classes. So if today you wanted to add a method to the string class in Java, you have to have a discussion with Oracle. In Scala, if you want to add your own methods to a string class, you just do it, and it looks like the methods are natively part of string. So some of the controversy is this can happen in the background and not always with the greatest clarity to somebody who's reading the code. No checked exceptions, so Scala has exceptions, but you don't have to declare them in the interface in Java. In general, exceptions are discouraged, and instead getting multivariate values back is the preferred style. Parameters can be pretty powerful. They default and named and variables, variable numbers of them. Override, in Java there's an ampersand override to help you from making a mistake, to accidentally miss overriding a method in a superclass. That's been such a good idea. Scala makes that mandatory. And it's a pure OO language in the sense that there's no distinction, at least from the programming model point of view, between primitive types and objects. Everything is an object, and all operations are methods. So some of my opinions, but before I share you my opinions, which probably going to differ from other software engineers, just share this quote by Bjorn Strustrup, the creator of C++. There are only two kinds of languages, the ones people complain about and the ones nobody uses. So some of the things I like, very concise, lightweight feel, very strong, yet very flexible, static typing, strong support for the functional programming model, and as I mentioned before, an important pragmatic bridge to Java and its libraries. Extremely powerful language, constructs if you need them. Very good tool support and good books and online resources, Coursera courses and those kinds of things. Some of the things I don't like, it's a big language. I'm going to address this in a little more, a little later, a moderately big learning curve. The other thing that bugs me about Scala a little bit is some of the things that irritate me about Perl. Perl has a number of ways you can express something, which is great if you're a writer. That's difficult if you're a reader because you got to know all the different forms to read. And Scala suffers from that. There are many ways to do some things, and you got to be aware of them all. As I mentioned, it's not a top 10 language, which is somewhat of a consideration in academia. It's an incredible consideration in industry if you look at making significant investments and looking at workforce availability and consultant availability and training availability and tools and on and on. And as I mentioned, it's a language that I wish my students came to my course already understanding. Java 8 is interesting because it introduces some functional concepts, most notably lambda expressions or anonymous functions, so it starts to get into the into the functional programming world as well. This is actually a benefit to Scala, not a threat in my view. Scala's will take advantage of the new functionally optimized JVM in Java 8 in its next release. One of the important things I've observed is I've seen a large pool of Scala programmers who say, you know, looking for my next job, it's going to be a Scala job, or at least a functional programming job. We're fortunately at this point, at the point in the economy, people can make those choices in many cases. But I don't know in my circle of Scala colleagues that of any programmer who's gone, Scala programmer who's gone back to Java, at least willingly, who didn't have a job that required Java. So wide variety of tools. This turns out the REPL to be extremely important advantage when we get to the Spark environment. This opens up the ability to program in an interactive terminal session environment where you get immediate feedback on operations, and is a great way to check out your programming code in little snippets, but also, as we'll see, to check out your data in snippets as well. There are a huge variety of unit test frameworks that support a wide variety of testing strategies, style checking tools, an alternative to Maven called SBT is a build tool, and as I mentioned, the Java compiler as well. So starting to shift a little more to big data. If you look at a lot of the big data technologies, we've got clusters of computing systems, and they have parallel resources of CPU and memory and disk, and a lot of the operations we do are split amongst those independent computing units, and they operate on those components in parallel. Well, that sounds a lot like a map method in functional programming, the ability to operate individually on pieces of data items in a collection. Most of the times that collection exists on a single system, but there's nothing that says that collection can't be spread across multiple systems. And eventually we need to do some kind of aggregation. We need to take all those spread out intermediate computations and merge them together for a final answer, like an average or a sum. And that corresponds, that reduction kind of operation corresponds to many of the aggregation operators in functional programming. So one of the things I see, especially coming from Java and OO language with the Hadoop technologies, which are kind of functional in architecture, is the fit of a functional language with that functional big data architecture makes more, less of an impedance mismatch in my view and what I've seen with my students as well. So coming from a Java base, if you wanted to take the journey to Scala, to pick up the OO features is really fairly straightforward, days to weeks, and you could be programming in Scala in an OO fashion. If you want to learn enough of the functional features in Scala, weeks to months, and you can be pretty darn proficient in a technology like Apache Spark. But there is intellectual fruit for a long period of studying. You can get deeply into the depths of functional programming and category theory and the higher level algebraic constructs. And the challenge I think that's really most important is most of us have grown up programming in imperative languages and in object-oriented languages. And I tell my students it really is a little like learning how to program all over again in a functional language. Some view that as a negative thing, others view it as an opportunity. I certainly fall in the opportunity camp. I think this helps make programming fun again if you become used to it for a while. So moving to Spark here, Spark it grew out of academia as well in Berkeley starting in 2009 and became an Apache project relatively recently in 2013. Its place in the big data space is it keeps data in memory where possible. And this is especially important for iterative algorithms that you might find in machine learning, in data mining, algorithms that operate on the same data over and over again. If they did that in the pre-Spark environment, you would pay I/O cost writing out data to disk and reading it in after every iteration. If you can keep that data in memory between iterations, you can get a dramatic improvement, 10 to 100x in some optimistic scenarios. There's a bit of Spark mania that Spark is going to take over the world. I don't quite fall in that camp. For the kind of application where you ingest a lot of data, you do a lot of processing on it and then write it out once, we really haven't seen a big compelling advantage over Spark. So it's really this these iterative algorithms where it really shines. So Spark, as I mentioned, is itself written in Scala. You can write Spark code in Scala, in Python, and Java. More recently, R has been added, and the SQL environment as well. There are other libraries, streaming, machine learning, graph processing, and so on. So there was a survey done a year ago, and it showed that programmers programming in Scala, 88% of them, or in Spark, 88% of them would choose Scala, 44% Java, 22% Python. If you notice, they don't add up. They add up more than 100%. The reason for that is some programmers program in multiple languages. What I'm seeing today is, I think if the survey were done, Python would definitely be in the second spot. We're really seeing Python emerge as a language of choice for the ad hoc data science programming, and Scala to productize that work in more of a software engineering environment. So Spark at its core runs at this level. The libraries I mentioned run on top of it. Spark can run on its own cluster management software or on Mesos or Yarn environment. The programming model consists of transformations and actions. Transformations modify something called an RDD, which is basically just a distributed collection. Transformations modify it from one state to another state. So mapping the values, filtering the values, all of those kinds of things are transformations. Sorting the values are transformation. Actions are aggregating the parallel collection, producing sums or averages or other aggregation operations. And what's interesting about this model, and this has impacts on my students, is that these operations are lazily processed. So you can do transformation, 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 and then do an action, and then that action triggers all of the previous transformations, all optimized at that point. So processed lazily. From a student point of view, they do an action and they see an error. They're focused on the line that did the action. And one of the things I'll point out is often they have to look back and see what kind of transformation, could be many lines of code back, was the root cause of the problem. Although Scala or Spark tries to keep data in memory, it'll spill to disk automatically if needed. So I'm not going to go through this code, but the next two charts show the classic word count problem, taking a text like all of Shakespeare and finding all the unique words and how many times they appear. It's kind of the hello world of the big data space. So these two charts show it written in what's called the Java MapReduce model. And most of this code is boilerplate. There's very little actual logic in it. And I'm now going to show you three charts of Spark code, first in Java, then in Python, then in Scala. So here's the Java code. Pretty ugly in Java 7. Java's 8 functional features make it look much more appealing. Python, fairly concise. This lambda keyword always bothers me and sticks out as verbose, but I think a good language to program in Spark. And this is the Scala interface for Spark. Very elegant. Most of the features in Spark come up first with the Scala implementations, and the others follow. But extremely important for productivity is this interactive shell I've mentioned. You can do this in Scala, you can do this in Python, you cannot do it in Java. Java does not have an interactive shell. So I'm going to show you an example of Wordcount. I'm not going to go through these in detail, but I'll give you a little sense for what Scala and Spark programming looks like. All processing starts with something called a Spark context. That's your hook to the world. And here we're reading in a file. This happens to be from a distributed file system. For those of you who know Hadoop, it's HDFS, Hadoop Distributed File System. So it gathers all of the files in that particular directory, which is actually only 3 little tiny files, each only a sentence long. And anytime I do collect, it says grab it from its distributed systems and bring it into local memory. So if this is a petabyte, you don't want to do a collect. But for small examples, this is fine. So I get an array of 3 elements where each element is actually the text document, in this case, a single string. And then I can do a map operation. And the map operation is going to split on that regular expression, which is basically a fancy way of parsing based on spaces and punctuation. And now what I get is an array of arrays of words. Well, I don't necessarily, in this word count application, want arrays of something. I just want an array of all the words that I see in my document collection. So there's an alternative if we take a step back and do a flat map we can flatten that array of arrays to just arrays. So now this is starting to look a little better. I have some case issues, and it's not clear how I'm going to count each occurrence of the words here. But if I keep forging forward, I can do another map operation to take care of the lowercase. So I do the lowercasing, and I'm creating what in Hadoop would be a key value pair, when in Scala is just a tuple with two elements. The word in the first element and literally the number 1 in all the second elements. And then I'm going to go and process those ones and reduce them. This is a little cryptic Scala syntax for keep going through the elements with a common key, with a common word, and sum all those ones together. So I get it now close to my word count. Matter of fact, the only extra thing I'm going to do is throw in a sort for fun so I can sort the words. So what I want you to get a feel for is, if you could place yourself in my student's point of position, not only can they use the shell environment to see if they're understanding how to compose their code, but they're seeing the results of their operations very quickly. So if there are anomalies in the data, at least in the samples that they're drawing, they can see those and react to them in real time, as opposed to writing static code again, compiling it, building the jar file, uploading it, and running test cases. So I would estimate the order of magnitude of this development over the Java MapReduce development is at least 10x. Matter of fact, I have a problem. Most of my students like this environment so much they ask, and I introduced this halfway into the semester, why I drug them through the first half of the semester doing Java MapReduce programming when they see how productive they are. And finally, we're going to write our data back out to the Hadoop file system. So first element read the data in, we did the processing, and then we wrote the data out. In this particular example, the data was partitioned into 3 pieces, and I can print it out and see my count here. And the nice thing about these programs is I can run them against Shakespeare's corpus, I can run it against Project Gutenberg, I can run it against Wikipedia, and this same code will work in parallel. Even though the one-liner fluent style of programming is fun to write, I often have my students break each step down into an individual variable, much easier for debugging purposes. And finally, once they finish with the interactive development, they can throw their code into a standalone program and then compile it, build a jar file, upload it to our cluster, and execute it. There's been a recent addition to the Spark language called Dataframes, models Dataframe ideas or pandas in other languages, and brings the Spark model much closer to the SQL model. So they're like these distributed databases, distributed collections, but they're ones that are optimized for, much like query optimizers work, to do data processing. So here's a simple little example of some playing around. I've created just 3 stock records, 3 New York Stock Exchange records. So the schema looks like the exchange and the stock symbol, the date, open, close, and so on. I'm going to read these records in by parsing, they're a CSV file, by splitting on commas. And then I'm going to fit them in something called a case class. So this is actually an illustration of a blend of the object-oriented feature of Scala with the functional programming feature. I'm going to parallelize it. That's going to distribute the collection across a cluster. And then I'm going to call just a simple method on the distributed collection on the RDD called 2df, and that's going to make a data frame. Now, if you come from a SQL background, this should all look exciting. You can do a count. You can look at the first element. You can show and get some old school ASCII formatted table here. You can print the schema. You can do group bys and counts. So approaching a data language, declarative data language. You can do filtering. You can then create a table. And now we've just bridged to the world where you can execute SQL statements, select symbol, close from stock where close is greater than 5, order by symbol, and then show the result. And we've now just bridged to the world where You don't have to write any Scala code per se. You just have a little boilerplate and can embed SQL code in it. And the other part of this story is there's built-in support for a huge variety of data sources. So doing something like processing JSON files is as easy as that one line of code, and I've created a data frame off of a JSON file. I can look at the schema, I can count the number of elements, I can do a query, show the city with a zip code of 55105, and just a couple lines of code, and we've processed that file. We can then output that file into a table, and now I've switched technologies. I've gone to a technology called Hive. Hive is a traditional Hadoop technology that brings SQL to big data. It does it by internally generating MapReduce jobs under the covers, and I can do queries and process in other ecosystem components seamlessly. So a great degree of integration with data sources and with the rest of the ecosystem. Let me just close with one summary of what my experience has been. So the way I run my big data course is half the semester is Java, MapReduce, and related technologies in the Hadoop environment. And then for the last year, I've switched over to 2 lectures, 3 hours each, on Scala and Spark. So students come knowing how to program in Java, know nothing about Scala, know nothing about Spark. They're able to complete 2 homework assignments, one with some guidance throughout it, one with very little direction. And the completion rate is like 95% on these assignments. They really like the interactive shell environment, the concise API, the expressiveness of the API, and the faster development time. In fact, about half the students say, you know, I picked my project at the beginning of the semester and I was going to do it in Java, and I like the Scala stuff, and I want to change my project to explore Scala and Spark. 2 hurdles I've seen. I mentioned this laziness point. Errors that you find in an action because of lazy processing could have been caused by a previous transformation, so that can make debug difficult. We're all used to when we do something and we get an exception, what we just did must have been the cause. Well, in a lazy environment, that's not true. And sometimes, since the Scala and Spark APIs are so seamless, it can be difficult for them to know what function they're using. Is it a Spark function or is it a Scala function? And sometimes get those confused. So with that, any questions or comments?
We got time for one question, if anybody.
Just, are there follow-on courses that are using Spark and Scala that kind of go through the curriculum, output professional Spark and Scala developers inspiring?
Yep, so we have a course that goes one higher level in the stack. So today it focuses on Hive, Pig, HBase, Cassandra, the higher level capabilities. That course will be, as Spark SQL matures, we'll be taking on that content. And we also do professional development. Matter of fact, we've had big demand in the Twin Cities for Spark training and actually for Scala training. So there's a major company that's just signed up for a 2-day Scala course when I get back. So we're seeing a fairly big investment. If you're not familiar with the Twin Cities industry, we got everything from the Targets, the Thomson Reuters, the Medtronics, the 3Ms, Boston Scientific, and so on. What's that? Best Buy, yes, Best Buy. Other questions, comments? All right, thank you.